All right, everybody. Today we're going to be looking at 6.2, which is called integration by substitution, also known as U-Substitution or U-Sub. Now, this is one of the most challenging topics in integral calculus because the integrals we look at are going to look really complicated, but we're going to be learning a method that allows you to simplify these integrals so that they can become simple. Now here's an example of one of those crazy integrals I was talking about. So consider the following very challenging integral in this example. The integral of negative x over the square root of 25 minus x squared, all with respect to x. Now in this situation, most people look at this integrand and they have no idea where that integrand came from. I mean, what function, if you took the derivative, would give you something like this? Well, sometimes when people are faced with difficult integrands, they just try something out. They try breaking this down into smaller pieces, like negative x squared over 2 as your numerator, and then, forsaking all of our quotient rules in this case, maybe dividing by 25 minus x cubed over 3. And if you just take a look at what I've written here, we know there's no way that could be the right answer. If you tried taking the derivative of that function that I've just written down, I mean, with the quotient rule and chain rule, it wouldn't simplify to give us the integrand in the problem here, so there's no way that could be correct. Now, sometimes when people look at these integrands, sometimes they see a formula. Now, if you looked at this one and saw, oh yeah, wasn't that, I don't know, something kind of like inverse sine of x maybe? Well, that's a nice thought, but if you guys remember the derivative of inverse sine, you end up getting 1 over the square root, so that part's okay, but you get 1 minus x squared, and again, that's not exactly what we have in that integral. So the question remains that this problem, when you look at that integrand, it causes issues because it's hard to come up with an antiderivative for it. So in situations like this, when you're dealing with an integrand that you don't recognize, in other words, an integrand that you don't know the antiderivative to, well, sometimes it involves looking at an old derivative rule that we had from first semester. So let's take a look at one of those old first semester derivative problems. Now, since integrals are antiderivatives, then maybe if we look at this old chain rule problem, it might help us with the integral we were just trying to solve. So let's figure out, just totally randomly, what the derivative of square root of, I don't know, 25 minus x squared would look like. So if we took that derivative with chain rule, hopefully you guys remember that we start from the outer function, which is the square root of something, and we start by taking that derivative, the outermost layer. So that would give us 1 over 2 times the square root of whatever we had on the inside. Now remember, with chain rule, you had to leave that 25 minus x squared intact right there. But then what we did was we multiplied by the derivative of this inner function. Now that the square root is taken care of, now we take a look at the inside and we multiply by the derivative, which is negative 2x. Now if you take a look at what we could simplify with this expression, we can cancel out those 2's, and lo and behold, we end up getting negative x over the square root of 25 minus x squared. Now that looks awfully familiar. The integral we just looked at had this as our integrand. So because the chain rule helped us take that derivative, well, really we need the reverse of the chain rule to take this integral. So now that we take a look at this integral again, when we figure out that this integrand here was really the derivative that we obtained by using the chain rule, that means when we're trying to take the integral here, we actually need that original function, in this case, the square root of 25 minus x squared, and of course, since this is an indefinite integral, we'll say plus c. Now, if you take the derivative of this answer that we get, then of course, just like we did a moment ago, you'll end up getting this integrand. Now, the introduction to U-substitution is to tell you that U-sub is the method that we use in any time we're dealing with an integrand that came from the chain rule. The toughest part, however, is seeing when your integral actually came from chain rule and how to use the method that we're going to learn to reverse it. So first, let's do a little recap on the chain rule. If you remember, the chain rule was the way that we differentiated composite functions. In other words, functions like g of x within other functions like f of x. So how do you begin the chain rule? Well, you start with the outer derivative, f prime, but you keep the insides intact. Then you multiply by the inner derivative, g prime of x. Now you're going to be seeing this a lot just because it helps to visualize the outer derivative and the inner derivative whenever you're about to use U-substitution. So as a quick example of seeing the outer derivative and inner derivative, if I asked you for the derivative of sine of x cubed, well, how do you begin a process like this? Well, starting from the outer derivative, the derivative of sine would be cosine. But what do we leave in there? We leave x cubed. Then you multiply by your inner derivative, which in this case is x cubed. The derivative of that would be 3x squared. So again, normally when we write these answers, we usually write the polynomials in front and then the trig functions afterwards. But the inner and outer derivatives should be very clear in terms of how we took that derivative using the chain rule. So now comes figuring out when U-substitution is needed. Based on the problem we just did, if you imagine using the chain rule in reverse, then what you need to look for is the inner derivative that comes from some part of the integrand. In other words, when you look at this integral right here, do you see a derivative that came from some part of the integrand? Look closely. Is there something here whose derivative shows up somewhere else? Is there something here whose derivative shows up somewhere else? I know, so subtle. So hopefully you are all looking at this x cubed here, which was our part of our integrand, whose derivative was 3x squared, which shows up someplace else. Now, I know I'm making a joke of this, but this is exactly what you have to identify in any integral now in order to know if U-substitution is the appropriate strategy. Do you have some part of your integral whose derivative shows up someplace else? Now, once you've identified that this is a U-substitution problem, here's how you actually use U-substitution. First, you have to say what U is. So in this case here, we're going to take our part of our integrand whose derivative showed up somewhere else, the x cubed, and we're going to set U equal to x cubed in this case. Now, once you do that, the next step is really important to get correct. I know we're in the middle of taking integrals, but you do have to know how derivatives work in order to use U-substitution correctly. So what is the derivative of U with respect to x? Well, that's just asking what's the derivative of x cubed. So that would be 3x squared. Now, a very important step in all this is to actually take this statement here and solve it for du. You'll see why this is important in a moment. But essentially, for this case, all that means is we need to multiply both sides of our equation by dx. What would that give us? Well, that would give us 3x squared dx. So now, with all this stuff we've just set up, these are the keys to being able to substitute correctly. These two equations here and here will allow us to take our original integral and make it a little bit more simple. So watch carefully as I now substitute in the pieces that we just set up. So I'm going to take the original integral and I'm going to rewrite it as a new integral. Let's actually start right here. If you take a look at cosine of x cubed, well, I want to write cosine, but instead of writing x cubed, well, I want to substitute x cubed for u. So in this case, I'm going to write cosine of u. Now for the next part, I want to take 3x squared and this dx over there, and I want to substitute it out for whatever 3x squared times dx would give me. Now if you notice right here, 3x squared dx, well that's equal to du. So I can replace both of those things with du. Look at this new integral we've just created. It's the exact same integral as before, with all the pieces substituted out to make it look more simple. There's no more x's in the equation, in the integral, it's only u's. And if you look at the variable of integration, we're taking this integral with respect to u. So if I were to take an integral now, I would much rather deal with the integral on the right, which integral of cosine of u du, that's simply sine of u plus c. So notice how easy that integral was to take, and the last step in this problem is simply to replace u right here with what it was in the original problem. Now we set up the U-substitution so that u is equal to x cubed. So all we need to do now is take sine of x cubed. We can put that in parentheses plus c. So there's our first real U-substitution problem that shows you how you can take the chain rule and reverse it based on the clues of how you substitute these pieces into the new integral. So now we're going to look at several examples of a lot of different scenarios in which U-substitution is the way that you can take this integral. Now this integral here looks a little frightening. The integral of the quantity 6x squared minus 5 multiplied by the quantity 2x cubed minus 5x to the 6th power dx. Now if you look at this question and you get concerned by all the different powers and all the different functions and expanding that might be necessary, don't worry about it. Look carefully at this problem. Do you see a part of a function whose derivative shows up somewhere else in the integral? Now again, look carefully here at our integrand. If you were to take the derivative of some part of this, would you see the derivative show up somewhere else? Now, if you think you spotted it, then what you want to do is set u to be the part of our integral whose derivative shows up somewhere else, and then take the derivative of it and get du dx, so that you see how you can substitute out the pieces you need. So look one more time very closely. What part of our integral here could you take the derivative of so that you would end up getting something else that shows up in our integral? Well, I hope you were able to see this. In this situation here, what's the derivative of 2x cubed minus 5x? Amazingly, it's 6x squared minus 5. This is the exact connection that you want to identify whenever you're dealing with an integral that might involve U-substitution. Forget about that power to the 6th here for a moment, and just take a look at the beauty of that connection. The derivative of 2x cubed minus 5x is 6x squared minus 5. So here's how you actually take this integral. Once again, take u and set it to be 2x cubed minus 5x. Again, don't worry about the 6th power. All you want to do is set u to be that part of our integral. So then if I said take the derivative of that, you would of course get 6x minus 5. Now please don't forget this important step here because of all the connections it's going to require later on this week. Once you take the derivative, please solve for du, which means you would have 6x minus 5 and then dx. So now comes the point in which we want to try to solve for this integral by first substituting out the pieces we need. So let's take a look at our integral rewritten using our substitution. So first of all, let's start with the 2x cubed minus 5x, the quantity raised to the 6th power. Well, since 2x cubed minus 5x could be substituted with a u, then I'm going to really write this as u to the 6th power. Notice how much easier that looks now? Now in order to make the substitution work, you also have to substitute out the 6x squared minus 5 and that dx over there. Lucky for us, we have 6x minus 5 and a dx right here, and we can replace all of that with simply a du. So I'll put the du over at the end of our integral, and now if you take a look, our integral is a very, very simple one to solve. This is a power function in terms of u, and so the integral will simply require the power rule. That would be u to the 7th over 7 plus c. So in the final step, what do we have to do with u? We have to replace it back with 2x cubed minus 5x, all raised to the 7th power, divided by 7 plus c. Now this answer here, everyone, if you were to take the derivative of it, just take a look at for a moment what would happen. The 7 here would come down in front and get canceled out with this 7 in the denominator and lower to a 6th power. Then the derivative of 2x cubed minus 5x would be 6x minus 5, which would have to multiply our answer. The c, of course, goes away, but look at how that would give exactly the integral we started with. 2x cubed minus 5x now to the 6th power, and then multiplied by the derivative of the inside. This is how U-substitution works. So here are the 5 steps to execute the U-substitution method properly. Now please pause the video right now, record down this information in your notes. I know it's annoying to write while I speak, so just pause me, write it all down, and then push play when you're ready. Okay? Pause. Okay, welcome back. Did you pause? Okay, here we go. Before you start, always determine if U-Sub is even the right strategy. You should not use U-Substitution anytime you see an integral you can't figure out. You should use it anytime that you see a part of the integrand whose derivative also shows up somewhere else. Once you've made that identification, then go through these 5 steps. So step 1, set U to be the function that shows up in the integrand whose derivative is also there. Then take the derivative of U with respect to x, and then solve for du. For right now, all that involves is multiplying both sides by dx. Later on this week, it's going to be a little different when we figure out how to make the substitutions work. Finally, substitute all the parts of the original integral using only the pieces with u and du involved. Once you've done that, the integral should be much easier to figure out, which means that you can evaluate the new integral, this time with respect to u. The whole point is to take a complicated integral and turn it into a simple one. The final step, once you've taken the integral, is finally replace u back with whatever choice you made back in step 1. Sorry, that's a typo, and I can't change it anymore. Okay, let's take a look at a whole bunch of examples now in all the different scenarios that U-Sub might come up. Okay, so here's our second example, and once again I want to stick with power functions because sometimes it's the easiest way to begin seeing how U-Substitution works. So once again, take a look at our integral here, and the challenge is, can you figure out what part of our function has a derivative that shows up somewhere else? Well, as we look through it, what's the derivative of 5x to the 4th? Well, that would be 20x cubed. Yeah, that doesn't help, does it? But what's the derivative of, inside these parentheses, x to the 5th plus 3? Well, that would be 5x to the 4th, which is exactly what I see in the front of our integral. So let's get started. What should u be? U should be x to the 5th plus 3. Now, if you were wondering why we should include the plus 3, it's only because it makes the problem easier. Without the plus 3 there, then the new integral that we write would end up being more complicated than it needs to be. So watch when we take the derivative, you get 5x to the 4th, and notice that plus 3 goes away. And now, of course, we want to solve for du so that we get 5x to the 4th dx. So now let's take this old integral and turn it into a much easier one. First of all, we don't need x to the 5th plus 3 squared. We need u squared. So already that part of our integral looks much easier. Then, so that's this part here. Now I'm going to take my 5x to the 4th and my dx, and I'm going to replace that with du. So look at how much easier this new integral looks, and in order to evaluate it, we can use the power rule, u cubed over 3 plus c. And in our final step, all we have to do is replace u with what we started with, x to the 5th plus 3 cubed, all divided by 3, plus c. You can go ahead and check that yourself to make sure that that gives us the original integrand when we take the derivative, or you can just trust me. Next. So here's an interesting example. So far, all the U-Sub problems we've been doing have used power functions. And if I saw x cubed in the integral and a 3x squared somewhere else, it makes the problem really easy. Now, trig functions tend to be really popular U-Sub questions because the derivative of a trig function is usually another trig function. So take a look at this integral. The integral of sine cubed x times cosine of x. Now, to be honest, the derivative of sine is cosine, and the derivative of cosine is negative sine. That actually makes this a very interesting example because we could use either one. Now, technically speaking, the easiest way to set this one up would be to set u equal to sine of x. Now, why would that be the good choice? Well, I would much rather deal with u cubed than sine cubed when it comes to an integral, because I can take the integral of u cubed without too much difficulty. So if I asked what's the derivative of sine of x, well, that would simply be cosine of x. And again, if we solved for du, we would get cosine of x dx. So now let's take a look at our integral here and see if we can rewrite it so it looks much easier. So instead of sine of x cubed, or sine cubed of x, I hope you guys realize that that's simply u cubed, because u is equal to sine x. And now this works out even better, cosine x dx, literally right there. If you guys notice, we can substitute that out for a du. So once again, our integral is a very simple one to get. This would be u to the fourth over 4 plus c, which is, once you substitute back in your sine of x, it's really sine to the fourth of x over 4 plus c. So a lot of these integrals have ended in the same way. Basically, once you figured out your u, you just use power rule to take your integral. Now let's take a look at some more examples that change things up a bit. So here's one of my favorite questions, and it's a very, very popular type of U-Sub situation. Anytime you are dealing with U-Sub and you see an exponential function, here's almost guaranteed what will happen. You'll see e raised to some function up there, and 99% of the time, that function's derivative shows up somewhere else in your integrand. So in this case, e to the tangent of x times secant squared of x. That integral looks horrible. But if you take my advice, just take u equal to whatever is in the exponent of your exponential function. That way, if the derivative, which is secant squared x, shows up anywhere, well, now you've got one of the easiest integrals to solve once you solve for du. So let's put that secant squared x dx like that, and now let's take our integral here. So our integral will be e, not to the tangent of x, but e to the u, and then multiplied by, well, secant squared x dx, that's simply du. What's the integral of e to the u du? Well, that would be e to the u plus c. So in the very easy situation here, all we need to write is e to the tangent of x plus c. Now just real quick, and we haven't done this for many of them, but let's just see what would happen if you took the derivative of e to the tangent of x plus c. Well, using chain rule now with derivatives, remember that's the original way we learned this, that would be e to the tangent of x, just like usual, times the derivative of tangent, which would be secant squared x. The plus c, of course, goes away, and just take a look at what this answer was, and now look back at the original integral. This is one of the most popular ways that you'll see integrals being asked anytime you see e raised to a function. Well, you knew this one was coming. If we're going to deal with exponential functions, let's also take a look at logarithmic functions. Here we have the integral of cosine of natural log of x, all divided by x. Now before we actually set up our U-substitution, just real quick, what's the derivative of natural log of x? Oh yeah, that's 1 over x. 1 over x. You know what? Look at our integral one more time. A lot of times you'll see in a problem, whenever you see a natural log in your integrand, you'll see an x, a singular x right there in the denominator. In those scenarios, here's the way you would want to approach it. Take u and set that equal to natural log of x. Why? Well, when you take the derivative, you would get 1 over x. And of course, solving for du would give us 1 over x dx. Now, why is that such a big deal? We'll take a look at this integral. Before I substitute anything, I just want to rewrite it so that you guys can see exactly what we're dealing with. This is cosine of natural log of x times, not divided by x, but times 1 over x dx. Do you notice I haven't written anything new? It's just simply the original integral rewritten. Now if I asked you to substitute out certain pieces, well, let's write cosine of, well, not of natural log of x, but cosine of u, and then instead of 1 over x dx, well, that can simply be replaced by a du. Look at how easy that integral looks now. So now we need to know the integral of cosine, which is simply sine of u plus c, and that means this problem, or the answer really would be sine of natural log of x plus c. Pretty cool how logarithmic functions can be used in U-substitution as well. So we're almost done, just a couple last examples, and they're both done the exact same way. There's a couple of U-Sub techniques that are just really convenient to know. In this case, what happens when you set U to be equal to the entire denominator? Well, in this scenario, why would you even want to do that? Take a look at this integrand. Can't we simplify this instead of using U-Substitution? Actually we can't. Look at the numerator, there's only one term, and in the denominator there's two terms. We definitely cannot split this up into two smaller fractions. So let's take a closer look and see why U-Sub is the key for this. Take a look at that denominator, x squared minus 15. Notice anything about it? Oh my gosh, its derivative is right here, 2x. Once again, these are the scenarios that you want to watch out for. So you set u to be equal to the entire denominator, x squared minus 15. And then if you took the derivative, of course you get 2x, and then if you solve for du, for our substitution, you'll get 2x dx. Now when you take a look at this integral now, be careful. If I were to show you this problem, the way that's easiest to visualize it, I'm going to take 1 over x squared minus 15 times 2x dx like that. So in other words, the numerator I want to attach with the dx, and I want to see the function as 1 over the denominator. So why is that helpful? Well, let's take a look at our substitution now. Instead of having 1 over x squared minus 15, we have 1 over u. And then instead of 2x dx, we have a du. Now the purpose of setting u to be the entire denominator is to actually get this integrand, because this is one that we know about. The integral of 1 over u is the natural log of the absolute value of u plus c. So in this case, our answer will be natural log of the absolute value of x squared minus 15 all plus c. So it's a pretty cool technique that works quite often. Whenever you have a fraction in the integral, take a look at the denominator and see if that function, if its derivative ends up showing up in your numerator. So here's one last example of how that works. Wait. What? Cotangent x? I thought I said something about a numerator and denominator. Don't we just have a formula for this one? Yeah, cotangent x. That's negative cosecant, right? No, not quite. The derivative of cotangent was negative cosecant x cotangent x, but not the integral. Let's see here. What trig function, when you take the derivative, gave you cotangent? Yeah, there wasn't anything, was there? Why is this showing up for funsies in our U-Substitution section? Well, what is cotangent again? Cotangent, well, tangent is sine over cosine. Oh, that's right. Cotangent is cosine of x divided by sine of x. Now look carefully at this situation. Look at the denominator. The derivative of sine x is what? It's cosine of x. You know what? That last question where u is equal to the denominator, that might be useful right now. So if you set u to be equal to sine x, then the derivative is cosine of x. And of course, du is equal to cosine of x dx. So if we write this integral correctly, let's write this as 1 over sine x times cosine x dx, just to see the substitution a little bit better. And so now if we substitute in the u's, we get 1 over u times du. Same integral as before, so we'll get the same answer, of course, natural log of the absolute value of u plus c, which gives us this answer, natural log of the absolute value of sine of x plus c. I swear we've seen this before. Oh, go get your yellow cards, everybody. On the back side, there are 2 formulas. Check it out, everyone. Now you know why the integral of cotangent gives such a weird answer, the natural log of the absolute value of sine of x plus c. Good luck, ladies and gents. I hope all this work makes sense. I'll see you guys tomorrow.